Now, let's say we placed 11 grams of ice into at 0 degrees Celsius into 100 grams of liquid water. So, to do a problem like this, I draw a picture. I got ice. I'm putting it into what? Water. It's 100 grams of water. The water is at what temperature? 20 degrees Celsius. The ice is 11 grams worth, and it starts at 0 degrees Celsius. 0 degrees Celsius is the melting point of ice. So it should be all solid in this case. The final temperature when you mix these together is 10 degrees Celsius. So it asks us to calculate the heat of fusion for water. Heat of fusion is the amount of heat needed to melt the ice, for example. So to do this, what equation do we use? The Q equation. Now, for the Q equation, it has to be from one thing's point of view. Okay? Would you choose liquid water or ice? Water. Water, you already know the specific heat capacity for water. So for water, you got 100 grams of water, right? Change in temperature goes from 20 to 10, right? So goes from 20 to, from 20 to 10. So 10 minus 20, it's a change in temperature. Specific heat capacity is 1. So 100 times negative 10 times 1 equals negative 1,000 calories. Now, does that make sense that the water is losing heat? Where's the heat going? It's going into the ice. So the heat is going into the ice. So there's negative 1,000 calories going into the ice. Okay? So if we have a negative 1,000 calories of ice, how many grams of ice do we have? Oh, we've got 1,000 calories going into the ice, so that's a positive 1,000. How many grams of ice are we working with? Just 11 grams. So if we take 1,000 and divide it by 11, this will tell us the number of calories per gram of ice. There's approximately 90.9 or approximately 91 calories per gram of ice. So if we had 1 gram of ice, we would have to add 91 calories to it to melt it completely. If we didn't add 91 calories, would it melt? No. What if we had 1,000 grams of ice? Would we have to add more calories? Okay, absolutely. So this is called the heat of fusion for water. From our calculations, the heat of fusion for water, okay, in this case, equals the energy in calories divided by the mass in grams. So in this case, we took Q divided by the mass in grams and got what's called the heat of fusion. Sometimes the heat of fusion is written in calories per gram like this. Another unit that it could be written in is, instead of calories per gram, what else can we convert grams into? Moles. So another unit that could be used is calories per mole. That would be a different number value, but it would be a constant for a substance. So let's suppose we had 1 kilogram of water. This is a separate problem. This is a little more challenging. We got 1 kilogram of water at a temperature of 45 degrees Celsius. So the first thing we can do is draw a what? A picture. 1 kilogram of water at a temperature of 45 degrees Celsius. It's mixed with 1.5 kilograms of methanol at a temperature of 20 degrees Celsius. So you pour these two things together, and it's asking what is the final temperature of this mixture. Okay? So, which one will be losing heat? Water or methanol? Water. The heat will be going from the water to the methanol. So, water will have a negative Q, methanol should have a positive Q. So now we just plug into the Q equation. For the water, the mass of the water is 1 kilogram, which is 1,000 grams. The change in temperature, it goes from some final temperature to 45 degrees. So it goes from 45 to some final temperature. That's the temperature change. The specific heat capacity is 1. Now, this Q value is going to be exactly the same for the methanol, except it will be positive. So for the methanol, there's 1,500 grams. The temperature final, minus 20 degrees. And the specific heat capacity of methanol, we would have to look that up on lesson number 5. Can you look it up on lesson number 5? What's the specific heat capacity of methanol? I don't know that. 0.58. Now, if you look at this, this is the problem we have. We had two variables, but are they the same? What are the variables we have? Oh yeah, they are the same. They're both temperature final. That's what we want to determine is temperature final. So all this now becomes is an algebra problem. Not that that's necessarily a good time, but we can do it. So let's go step by step with how we would do this. Okay. First thing is we want to try to get the numbers on one side and the letters on another. So we're going to divide both sides by 1,000 and both sides by 1. 1,000 and 1. So that cancels out this value here. We get 1,500 divided by 1,000. Okay, times 0.58. This equals 0.87. That's times temperature final minus 20. On this side, we have negative temperature final plus 45. So now we distribute the 0.87 to both sides, to the right side. 0.87 times temperature final minus 20 times 0.87 is negative 17.4. And this equals negative temperature final plus 45. Okay. So when you have a variable without a number in front of it, you can assume the number in front of it is 1. So we add plus temperature final to each side. This means this is going to be 1.87 temperature final. And then we add 17.4 to both sides. 45 plus 17.4, this equals 62.4, equals 1.87 times temperature final. We divide by 1.87 each side, and the temperature final you get is 33.3 degrees Celsius.